And we just started. Yeah. So it's really a pleasure to welcome this afternoon Vincenzo Ripepi, who is not only a colleague, but also a good friend for many of us. And many of us know him since a long time. But anyways, let me make a brief introduction for Vincenzo. Vincenzo is primo ricercatore at the Observatory of Capodimonte. He got his PhD in 1997 at the University of Calabria. Then he moved as a postdoc in Naples, where since 2000 he's a ricercatore. And then since 2020, Vincenzo is the primo ricercatore there in Capodimonte. His expertise covers a wide range of topics related to stellar astronomy and astrophysics. His PI or QI of several observing campaigns at different telescopes from small size to 8-meter class ones. And I think that this is what we'll cover also, will be partly covered during his talk. And a very long title is Metallicity-Dependence of Classical Cepheids Period-Luminosity Relations on the Extragalactic Distance Scale. Okay. And sorry, and so
fancy results are on.
I wrote that, but I read it. So thanks for being here, and I'll give you the time in 40 minutes. You have 45.
It's a pleasure also for me to be here. To say there are so many friends. Yeah, so it's a pleasure to speak about work that we started a few years ago, and I would like to speak today about a particular aspect of the use of classical Cepheids as distance indicator. In particular, it's a long-standing problem concerning Cepheids, and it is the metallicity dependence of the well-known, well-famous period-luminosity relations for these pulsators. Okay, this is a brief outline of the talk, the introduction, and why Cepheids, then why it's important to study metallicity dependence for the period-luminosity relations, and then I will describe our project, which is devoted exactly to this topic, with the study of the metallicity of Cepheids, our present baseline results, and what we will expect to obtain in the future. Okay, let's start with classical Cepheids. All are familiar with these pulsators. They in the color magnitude diagram, they lay in the classical instability strip, which is this one. They are very luminous objects, absolute magnitude between -2 and -6, so they can be seen long distances. They are central fusion varying stars, so they belong to an evolution phase that we more or less understand very well. And they have long periods, they span a wide range of periods from very small to very long periods, and they are young objects. They belong to this population of our galaxy. The age is between 50 and a few hundred megayears. They can pulsate in fundamental, first overtone, second overtone, and also mixed modes. These are the typical light curves and radial velocity curves for fundamental mode and the first overtone mode. As these are the Gaia bands, and radial velocities also come from Gaia. Cepheids are important because they have this period-luminosity relation, which have been discovered long ago by this Leavitt, and this is the original period-luminosity relations. At the beginning, it was a linear in a period. Then they discovered that with the logarithm it is linear, so it's more useful. And since then, they are the most important distance indicators up to, let's say, 30 megaparsec now, 30, 40 megaparsec. This is a modern version of the Leavitt law. The period-luminosity relation is also called Leavitt law. In the large and in the small Magellan cloud, this has been found by Miss Leavitt in the small Magellan cloud, but since then we made progresses. And this is the modern version from the Ogle team. We see the period-luminosity relations for the fundamental, first overtone, second overtone, the third overtone, which is only possible in mixed modes. There are no single third overtone modes, so it's not important. Okay, some properties of the period-luminosity relations. We see that going from the blue to the near infrared, so B, I, J, H, K, we see two things. First, that the slope becomes steeper and steeper, going towards the infrared. So, of course, if the relation is steeper, is easier to use. And this is more importantly, the dispersion is lower going towards the infrared. We see also this here. Okay, I don't have time to go, but this is physically explained, so we know why. No, but I don't have time to go into the details. But this is the reason why we and also in the context of the distance scale, it is preferable to observe in the near infrared. Okay. Another important quantity to introduce is the so-called Basenite magnet, which is not the name of person, but it is a German word that means essence, real nature, introduced by Barry Mador in 1992. It is very useful quantity because by construction, if we know the R quantity, we can define the Basenite in this way, and this quantity results to be reddening free, as far as we know well RD, of course. Okay, and this is very important point because, of course, when we want to use our Cepheids in different galaxies, it's difficult to estimate reddening in different galaxies. So having a quantity which is reddening free is very, very useful. And this magnitude actually had a huge impact in reducing the uncertainty on the H0, the measure of the value of the H0, which we shall see. And indeed, a particularly important Basenite magnitude is that used in the context of the Schuss film, which is by the Nobel Prize of Andrews, and this is the magnitude which is commonly used to estimate H0, and is defined this way. These are the HST, now JWST H band, and these are the corresponding, the filters in HST correspond to the INAF band. Okay, classical Cepheids are standard candidates. Standard candidates is a term used by, also this term has been used by Miss Leavitt. And what are standard candidates? Are objects for which the absolute magnitude is known. And they also must have a small dispersion in the absolute magnitude and to be visible at long distances. And all these characteristics are possessed by Cepheids. So what is the standard candidate for Cepheids? For the Cepheids, it is the peer relation, because we need N. use them as distance indicators, and M is given by the period-luminosity relation. Of course, given this form of the period-luminosity relation, we have to calibrate the A and B constants in some way. Okay? B, for example, can be obtained, for example, in the imaginary cloud, because the stars are all at the same distance. But A must be calibrated independently and must be calibrated with geometrical methods, particular parallaxes, or, for example, detached eclipse binary. The use of Cepheids in the distance ladder to measure H0 is a three-step process. This is one of the versions, of course, is the version which is the version of the shield group, which is at the moment the most accurate. First, we have the first step is to calibrate the period-luminosity relations of classical Cepheids locally using geometric methods. Then we go to the second step. The second step consists of galaxies in which we have both Cepheids and supernovae type 1a. In this way, we can calibrate the absolute magnitude of supernovae 1a, which are secondary indicators, Cepheids are primary indicators. And then, once we have calibrated the supernovae 1a, we can go to the Hubble flux and obtain a measure of H0 by measuring the distance of the galaxies and the ratio. This is more quantitative, more in a more detailed way how this works. This is a very famous video. We have the first step is concerned the calibration of the period luminosity, in this case, period Basenac relation locally. Locally, we mean with using the three anchors. The first anchor is the Milky Way, and in the Milky Way we use the Gaia parallaxes. The second anchor is the LMC, where we use the distance of the LMC obtained from the detached eclipse binaries. And the third anchor is NGC 4258, where we have a maser orbiting a central supermassive black hole. And these are the three anchors which can use the simultaneously or singularly. Okay. So with these anchors, we can calibrate the famous A in the relation I showed before. Then we go here where we have at the moment 42 galaxies in which we have both Cepheids and supernovae 1a. We use the relation calibrated here to calibrate the supernovae 1a, the magnitude of P, and then we can go through the Hubble flow here and measure H0. So everything okay? No, everybody knows that this method gives a value of H0, which is around 72, 73, 74, but not values lower than 72. And this is in strong tension with the value of H0 obtained from the cosmic microwave background, coupled with the lambda dark matter theory from the measures from the Planck satellite. And this tension is seems to become stronger and stronger, and this could imply a crisis in the physics. We use up to now to describe the universe. So it's important to this was the very basic motivational work, to study all the systematic source of error in the cosmic distance scale. And one of these has been historically the metallicity dependence of the period-luminosity relation. Okay. Okay, let's see. What do we know from quantization theory about the metallicity dependence of these relations? Theory tells us that the surface stability strips shift towards cooler temperature if the metallicity increases. Okay, and this, since the PL relations are in some sense some the stability strip, this has an impact. And we see here a simulated period-luminosity and relations in different bands for different metallicities, and we see how they change with the metallicity, the slope changes, and also the dispersion, you know that, and there is also nonlinearity in the optical, so additional motivation to use the infrared. Okay, so the period-luminosity relation in the context of the measure of H0 is considered universal. And the same slope is used both locally in the Milky Way, in the LMC, and DC 4258, and everywhere. But is this true? Theory says that the slope depends on metallicity. Okay? Especially going from the solar metallicity towards the metallicity of the LMC, SMC, and even more metal poor region, the slope changes. Even if the main change is between the solar and say the LMC metallicity. Okay. While going towards the metal poor region, the change is less significant. Also, the slope changes less in going towards the red colors. We can also think about the changes with the helium content, because the Z changes also why is expected change. But what theory tells us is that if the slope decreases as Z increases at fixed delta Y on delta Z, but the slope increases as Y increases at fixed Z. So, in some sense, the two effects compensate one each other. So, at least if we don't go to very over solar abundances, for the moment we can forget about it. Okay, how do we parameterize the metallicity dependence? In this way, we have the absolute magnitude, then we have, depending on the particular bands we use, the intercept, then we have the slope of the relation, so the quantity that multiplies the period, which can be also depending on the metallicity in this form, and the effect of the metallicity on the 0 point. This is the more general, the most general formulation. Then we can ignore delta, as the sheet project does, and use this simplified version where the metallicity effect is only on the intercept. Okay, I will speak a lot about this gamma. Okay, so gamma is the metallicity, the metallicity term. Okay, how did in the past, people measure the metallicity effect. The idea was to observe the different regions of external galaxies. So the stars, the Cepheids are all at the same distance, okay? So we know that from our galaxies that the disk has a metallicity gradient. So if we go towards the external regions of the disk, the metallicity might be lower than towards the center. Okay. So we can measure the P relation here and the P relation here, and the only difference between the two intercepts, since the distance is the same, the only difference must be due to the metallicity effect. Okay. These are three different measurements obtained with HST from different authors using sometimes the same data. And we see that we have three completely different results. So this method is not very efficient. More recently, this is the formulation of the Shoes group. The Basen and tell that this, apart from the notation, this gap. Okay? The metallicity term is an output of all their big machines that put everything together, and one of the outputs is the metallicity term, and they have this value of gamma. Okay, minus 0.217 is the Bayesian result. Okay, so keep in mind this number. This is of the order of minus 0.2. Okay. So it's a rather significant metallicity term. But let's see. One of the points of the Shoes group is that they don't care too much about the metallicity-dependent, because they say our anchors and the supernova host galaxies, where we have both the Cepheids and supernova 1 type 1a, share the same metallicity range. So if we think about their use of relative use, even if we don't know very well the metallicity dependence, the error is small, has not a big impact on H0. So they, the result of their error analysis that the metallicity term has practically no impact compared with other factors. Yet, to reach 1% precision H0, we must understand accurately the period-luminosity dependence on metallicity. This is also they also understand that, and they continue to work on this also. This is one of the results from their group. That this is what is led by this Brewal, and there is also another paper on these days, and they try to measure the metallicity term using a different method. So they use the Milky Way. They find the 0 point, the intercept of the relation in the Milky Way using Gaia parallaxes, the LMC and SMC using the eclipsing binaries, so geometric distances. And they say, okay, if we write the 0 point, the intercept in this way, we have the metallicity on the x-axis, the intercept on the y-axis. If we parameterize this way, the slope of this line is gamma. Okay? And they find in this way this term on average this is in JK. And this is between 0.2 and 0.3 in different bands. Okay. This method has, in my opinion, problems. The first problem is to consider the Milky Way with a unique metallicity. Okay. They use Cepheids around the sun, so the metallicity is of the order of the solar ones, or plus minus 0.2 in iron average. And this means, but if we go, for example, if the sun were not at 8 kiloparsec from the center of the galaxy, but were at 12 kiloparsec from the center of the galaxy, the Cepheids would have very much smaller metallicity. The Cepheids in our galaxy span a range of more than 1/10 metallicity. No? So it's rather arbitrary to put this stuff here. Why not here? No? Okay. Let's go. The theory also predict a metallicity term rather smaller, rather in agreement with the Schulz group. Okay. In any case, in this plot, I report the gamma term from several authors in many years of investigations, and these are the two typical values, minus 0.2 and minus 0.4. And we see that there is still some uncertainty at that point. Okay. The metallicity effect can be, as we said, both on the 0 point and on the slope, but even if it might not be critical for the estimate of H0, it is still relevant for measuring the distance of individual galaxies, so absolute distances. If we want to measure the distance of M31, we must use the correct gamma value, no? Because if delta gamma is 0.2, so 0.4 instead of minus 0.2, minus 0.4 instead of minus 0.2, a very common error in iron average of plus minus 0.2 would be 0.04 in delta mu, in the distance modulus, so 2% in distance, which is a lot. Okay. And so we want to understand where this, we want to constrain where this value of gamma. Okay. Let's say apart from H0, might not be important, particularly important H0, but in general, to measure accurate distance, we must know gamma, and also not less important, it is important to understand well the physics of Cepheids. We want to know if we understood well the physics of Cepheids. Okay? That's why a few years ago we started the project Cepheids C-MetaLL, Cepheids metallicity in the Leavitt law, which the scope of studying the metallicity dependence, the Cepheids Period-Luminosity interactions. How to do that? We decided to use a different approach, to use a direct method. The direct method is, we have Gaia now, so we have the distances of the Cepheids in the Milky Way. We know that the Milky Way has a range of metallicities. You just have to go sufficiently far away from the sun to get metal poor Cepheids. We have Gaia parallaxes, we have metallicities. We can just fit our period-luminosity relations, period-metallicity relations directly. Okay. No need to go to LMC, SMC. to use different indicators, so to be more homogeneous in this sense. One of the problems in the previous work was that they just Cepheids around the sun, so with a very small range in metallicity. We want to go to use to find Cepheids with metallicity much more metallicity. And to this aim, we started to observe with high resolution spectroscopy a sample of more than 300 Cepheids, which is the same size of the Cepheids with metallicity known from high resolution spectroscopy when we started the project. Okay, at the same time, to be more as homogeneous as possible, we wanted not only to carry out the spectroscopy, but also photometry. In this, for these bands, G, I, Z, J, H, K, to observe all the Cepheids with the same in the same system. Okay, this is the team of the C-MetaLL project, and okay, to rush was okay, these are the telescope we used. It's not particularly important. The number of objects and heights and so on is not particularly important. Just to say that we already published 114 metallicity for Cepheids, and we have now paper on archive with additional 108. Okay, we already published earlier results using only 49 of our spectra. Spectra for 49 Cepheids, and complemented with a sample of Cepheids from the literature. And we found already in our first paper a metallicity dependence which is large with respect, large in absolute value. So of the order of minus 0.4, minus 0.5, compared with minus 0.2 of the choose group. Okay. These are the spectra we published in our second paper, and where we obtained the spectra for very metal poor objects, as metal poor as the SMC or even less. Okay, these are the results of for the metallicity gradient. It's not important. These are the current baseline results of the project. In our fourth paper, we used a sample of 114 stars from our sample of our spectra, complemented with the literature, and our, can be seen here, our spectra extended the metallicity range towards the metal poor range. While for the photometry, we used mainly literature data. This distribution in the galaxy important. What is important is that these are the parallax properties of our sample. One problem in going in the external part of the galaxy, where we have metal poor objects, is that they are also not distant. And therefore, the error in the parallax is larger compared with the errors we have around us, of course. That's why we want to compensate this with the statistics. You know, if we add the stars, we compensate the errors with the statistics. The other point is that due to the fact that going towards the external part of the galaxy we have all the populations. The star formation is less active. Also the Cepheids are on average older, and if they are older, they have lower periods. So it's difficult to completely cover the space of the parameters. No, we must have not only a large span in metallicity, but also in periods to cover completely. And this is a bit difficult. We have all here, no? Long period and low metallicity. By construction, because the galaxy is done in this way, so we can't change it up. I don't have much time, but now I have to speak a bit about Gaia. Gaia, the parallaxes of Gaia should have zero parallax for the quasars, okay? Because the quasars are very far away. But this is not true. Okay, we always find an offset compared with the quasar. This offset was 29 microsecond and 19 microsecond in the R3. Here we see the dependence of this offset from magnitude, color, and ecliptic latitude. The Gaia team devised a correction, which is called the parallax zero-point offset, which must be added, in this case, subtracted, because this quantity is negative, because the astronomer always do the things the opposite as the normal way. And so the true parallaxes are larger than the measured one, okay? And these corrections are individual corrections. Each star has its correction to obtain the true parallax. This has been calibrated in some way, okay? But, and these are different calibrations which all agree more or less. So, problem is that people found that these individual corrections were on average too large. So we have to apply a global counter correction, okay, to make these parallaxes, which now are too big, report them to a lower value. Of course, we sum this counter correction, which is negative, of course. Okay, always the opposite. So this counter correction can be measured in some way, but it is now one of the main source of error, the main source of the measure of H0. Because if we don't know very well this correction to the parallaxes, this has an impact, direct impact, okay? Because parallax means distance, and distance means directly H0. Okay? The relative errors are the same order, are the same. Okay, this is the correction for our. How do we treat the data? We cannot invert the parallax. Okay? Usually, you say distance is 1 divided parallax. Okay? You can do that because the parallax is a distribution of measurements, and to preserve, you have also negative values of parallax, which are perfectly fine, and you can do the logarithm, of course, and you have to preserve statistical properties of the parallax, you can't invert them, okay? Because the inversion wouldn't preserve the statistical properties. Therefore, we use a definition of the astrometric-based luminosity, which is defined in this way. In this way, parallax, okay, this is not this omega. The parallax is used linearly. Okay. Here we have the period-luminosity relation, period-luminosity-metallicity relation. And what we fit actually is this quantity. We have the parallax which is observed, the relative magnitude of basenite which is observed, the metallicity is observed, the period is observed, and the unknowns are alpha, beta, delta, and gamma, if we try to fit delta. These are the basenite relations we used. In particular, we also have the shoes one, okay? One is directional, but also other combination, the Gaia bands and the near infrared bands. Okay, these are all the tests we did, but it's not important now. So what is important is that these are the results. So we have 910 Cepheids. We span a range in metallicity, which is 1.5 depths, okay? So we can fit this metallicity dependence in a sound way. Here we have in this on the left and on the right also we have the gamma minus corrected, so the 0 point corrected for the metallicity. And what remains is the dependence of the period, okay? The colors are the metallicity. The stars are colored according to the metallicity, and we see that all the colors are mixed. So we corrected for metallicity. On the right, it is the opposite. So we removed on the y-axis the dependence on the period. And what remains is the dependence on metallicity. So the slope of these lines is the value of gamma. Okay. This is the same for the basenite relations. These are the main results we got. In this part, we have the calculation including the dependence on the slope, and on the right, without the dependence on the slope, just on the intercept. The lines here, the two lines are the minus 0.2 and minus 0.4, and 0.2 and 0.4 values. And these are here for the delta is the no dependence at all. What we find is that in general, we have gamma values of the order of minus 0.4, minus 0.5. So definitely larger than what is found by the shoes group. The delta term, so the dependence on slope, there is no clear evidence of its variation. Apart from, curiously, the basenite of the shoes group, which is this one, indicated with the another. So this is what we found. Okay. We made a lot of tests to understand if the discrepancy between us and the shoes group is due to how we did the fit, etc. And no, we always find the same result. And there is but there is another problem. The problem is that if you remember the counter correction, so the global correction we apply to the Gaia parallaxes, it has, of course, an impact on the metallicity dependence because it impacts at the 0 point. So they are correlated. and we don't know very well which is this value. We have all what we showed before, we showed before was without this global counter correction. Okay. Now we can wonder if we use a global correction, for example, of the order of 14 microseconds, which has been found by the RIS group, and an even larger global correction, 22 microseconds. What if this global correction can reduce the metallicity dependence and in this case reconcile our results with those of the Swiss group? And actually, if we use this counter correction, the gamma term reduces. But we now can use the LMC to verify our results. No, we haven't used the LMC in our so we can use it to validate the results. And what we find is that if we apply our relations to the Cepheids in the LMC, we can only recover the right distance of the LMC, so the geometric distance of the LMC, only if we have a gamma term of this size, so a larger metallicity term. Okay, so our conclusion is that at the moment our data says that metallicity term is of this order. Okay. Okay, I don't have time to. This is the photometry we obtained and other results. I go to the summary. So our results rely a lot on Gaia. Problem is that we have still this systematics on the parallax at 0 point, which has impacted the results. And we are all waiting for DF4, every improvement on that, but we still have to wait 2 years. Actually, the new parallaxes are still present, but of course they have to be. Nobody can do nothing with these parallaxes. We have to wait for the release. Concerning our project, the metallicity dependence of the luminosity and period-Luminosity relations, we already obtained significant results. And our results are that gamma is larger than what is present in the literature. We have to understand why, and we will continue to work on that. And in particular, I have other slides, but I cannot show them. What we want to do to improve this is to use just our spectroscopy. Now we have a wide sample, about 300 Cepheids with spectroscopy, homogeneous spectroscopy. So in our next work, we won't use literature, which could create this homogeneity the results, and we will only use our data. In this case, our data is as a continuous metallicity. We have the same number of pulsators at almost all the metallicity, always finding more than one that. So we hope that our next results will be even more sound with respect to what we have obtained up to now. Let's see.
Grazie Vincenzo. Before other questions, if you want 15 minutes to say something, to skip it, you really want to say.
No, just the new data set, because it's in the paper we have on the archive, we showed this, there is also this picture. In particular, we measured at Cepheids at minus 1.35. As far as I know, this is the most metal poor Cepheid ever measured, and this is the new. We can use our data to put constraints on the structure of the arms and other interesting stuff. For example, perhaps we can speak about it. Here there are experts on that. We find strange distribution of scandium, copper, zinc, and zirconium. But we can speak about that afterwards. Okay. And other problem. For example, another point is the alpha elements. Because going towards the low metallicity, also the alpha elements change. So another thing to explore is if this has an impact on the metallicity dependent. So
okay. So questions from here, or unmute yourself from the remote, and there is a question from inside.
I agree with you, the question for the policy the distribution that is to understand the result of the story so the mechanism is more or less of a business issues. But according to the one, you find that the stocklet is a factor of 2 larger than the could be due to the fact that you are expanding the range in very large. This stocklet appears many objects in the distribution. So this very false of the field is the test. Have you made the statistical random start from the
yes, we did exactly that. I haven't time to show this. I have the slide. Yes, we divided our sample in beams and used the same number of stars randomly chosen. We did many experiments. We used the same number of stars in each beam of metallicity, and the results are completely consistent. So this is not in any case. Now our sample is, this is our sample, new sample, only our data. You see, we have the same number of stars in all metallicity, in every metallicity.
The other point is that something we can learn is to do so if we use the output that we are taking, we are able to only this choice of output, we are able to reproduce the right distance of patterns. If the technology is they listen something. Indeed, the LC is also a conversion point which is for calibration. And then we also take the right distance for the LC. So it's important.
The point is that they have I can show you this part. There is some magic in the magnitude because if we look at their okay, these are the resonant magnitudes. Look at this. These are the different resonants, okay, in the near infrared. Okay, this is Gaia band. Okay, the different colors are 3 different counter corrections. Okay, no correction, the correction by rays, and the counter correction our another line. Okay, line. This is the shoes correction. the choose value, the choose basenet. And magically, the right LMC distance is obtained with the counter correct.
So the fact that you obtain the right distance is related to counter correction.
Yes.
But it doesn't mean that the counter correction is calibrated exactly what we use.
No, to counter, we can use. They use the different method because when you do the okay, so when you do the fit with the parallax, you can add the term, which is the 0 correction. So you can add it in the fit. And they did that, but they did that using the 75 Cepheids, for which they have HSP photometry. Because they only use HSP photometry to be homogeneous, to be consistent. So they have the same photometry locally and far away. But these 75 objects are around us. So they just span 0.4, 0.45 depths in iron average. That's how they calibrate that, obtain that 14 microamps.
And then they also have a question.
As a bit curious, the mechanism for that,
Also, yes.
but only for part of the because the Gaia has problems with the metallicity and having the spectra, or because they were not released, or
No, okay. I have also for that I have slow slides, but I can describe. In fact, no, they have more than 1,000 measurements, but of course most of them were for the same stars for which we have high resolution spectroscopy. In those cases, of course, we prefer, but we have verified that for the overlapping stars, also the metallicity were the same, more or less, no? And that was the case. That's why we used also Gaia, which is not high resolution spectroscopy, not true high resolution spectroscopy. But the results for the stars in common with high resolution spectroscopy were good, so we could use them. And real large back, since again, metal poor objects are far away, the Gaia results degrade immediately as far as you go more metal poor than -0.03, 0.3. So we can, in the end, the Gaia data don't add much because they are metallicity in the solar vicinity metallicity in this sense. In the new one, yes, because most of them, a collaborator of us, Anupan Bhattacharya, observed them in the collaboration with this to have also metallicity in homogeneous set, no? And we, our group, used the data. So they have been included in our test. Yes, yes. As I said before, around 0.45 includes the range. About 0.4, 0.5. Around the solar day, around the sun. Yeah, some are over solar and under solar.
The assumption assumed
No, but the problem is that it's a case that the sun is very pixel.
no.
You see the point?
No. If we can try to understand why this factor, if you can try to there is a lot of boosting we analyze the same analysis made one correction, selecting the start that the producer.
No, but I think that for sure, if we do the same, we will find the same results. If we find the same, if we carry out the same analysis, we will find the same result. Yes, but the difference is not large compared with the previous spectroscopy. Everything is in paper by Anupam Vansuraj, our paper number 5.
Just thinking for the future, do you think that you have more advantage to solve the problem of metallicity that we call it rate? If you use a large survey, let's say LS16 or better, or you will have more improvement by new generation of spectroscopy like WST or big collective variant with a precision, improve the precision of the spectrum and the metallicity. So we expect more improvement and more accuracy of the data of the statistic of LSST or large sample that now kind of
LST probably won't have a big impact on that because it's observed the optical. The problem is that we don't have near infrared photometry, especially in the north. Not as we can use a RAM from the south.
To have an infrared
We need the homogeneous infrared photometry. So infrared photometry, let's say a Rubin survey in the infrared. So with repeated observations in the infrared, that would be very, very important. For example, it's not clear if the Roman telescope will do a survey of the galactic plane. At the moment, it's not
Vista, the first survey.
Vista, Vista already, Vista is out. It's no longer observing because now foremost of the telescope. And but Vista already did some work on that up to 15. And of course, yes, we already have some data, VVV survey, but they have repeated observations only in K and only a few in J. And I think nothing in H. And unfortunately, now H is important because of this HST Vasna. So, of course, next generation of spectroscopes are foremost. For example, we'll observe main Cepheids in the galactic plane. But I think that yes, we have to add, we should add, we should add metal core objects, especially at long period. And there are only few, but it is quite impossible even for formats because it is in the optical. And if you go far away, even in the anti-center direction, you have a lot of dust. And in the optical, Cepheids are faint, and you can't measure them. You have to go to the infrared. You need a big telescope with the infrared spectrographs. For example, hybrids, for example, which is not relevant for us.
Okay. Very short last question. How does this gamma change improves the understanding of the Hubble tension? I mean, does it go in the right direction or in the wrong direction? Very.
You mean if the gamma is larger?
Yeah. Does it help or not?
Not much.
Doesn't change. So that's not the reason.
No.
Okay.
No. I think that in this respect, Adam is right.
Okay. Let's thank again Vincenzo. Obviously, Vincenzo and Marcella are here until next Tuesday, and so we have time to talk with them. And Marcella will have a talk 2 days from today. And this 1 week from now, we also have Brentali, so we have 1 week about distances.
No.
La pastiera? Yeah, right. Sì.
Sorry for the online people.